All of you. I just wanted to give you a chance to kind of go through this set of notes on potential energy diagrams, which are also referred to in the textbook in the AP curriculum as a reaction energy profile. So I wanted just to have you fill in the notes, but also get a chance to actually explain it myself a little bit to help you understand it. I'll post a couple other videos too, just because I won't be able to spend as much time as I would if I was in class with you today. So thanks for hanging in there with me. All right, so a couple things to kind of recall from what we've talked about before with bonds and energy that's involved, just because it's going to tie right into understanding the general setup of these potential energy diagrams. So what do we already know that happens in terms of energy when bonds are broken? Well, we know that energy has to be absorbed if bonds are broken, which means the energy of the system as bonds are breaking is going to increase because they're absorbing energy. What happens then in terms of energy of a system when bonds are formed to create the products? We know that energy is released as bonds are formed, so the overall energy of the system for that process is going to decrease because it's releasing energy. So in an overall reaction, and remember in an overall reaction we have both bonds breaking and forming, how does the energy involved with breaking bonds compare to those involved in forming bonds for an exothermic reaction? So if you think back to when we had our bond energy topic, we know that it's the energy involved with bonds breaking minus those for the bonds that are forming. So if it's an exothermic reaction, we know that there's more energy released to form bonds than was absorbed to break the bonds. So in an exothermic reaction, the overall system's energy has decreased and the products will then have less energy than the reactants. And keep that part in mind. For an endothermic reaction, we know it's the opposite. There's going to be more energy absorbed to break bonds than was released to form any bonds in the products. So the energy of the overall system is increased. So in an endothermic reaction, because the overall system is increased, the products would have more energy than the reactants. So pause the video just for a second if you would like and just see if you can look at these potential energy diagrams on the next little part of your screen right here and see if you can identify which is exothermic and which is endothermic. All right, so let's check to see how you did. The graph labeled A over here is going to be our endothermic graph that would have a positive heated reaction. So you can read this as this is where the energy of my reactants is. You can see this is potential energy. As they absorb to start to break their bonds, the energy of the system is going to increase, and then they're releasing energy as bonds are formed. This is our endothermic process because it took more energy to absorb to break bonds than it took to release the bonds. So the products end up with more energy, and that's where we get our positive delta H. For the graph that's labeled B, this is our exothermic process. We have our reactants, they're going to absorb energy as they break the bonds and then release energy when they form bonds. That releasing of energy is greater than the one that it took to absorb energy. So overall, the energy of the system has gone down, the products have less energy, and we would have a negative delta H. Ooh, sorry, change that little part there for this part. So when we read these potential energy diagrams, usually we're reading them as the forward reaction when we're reading the chart from left to right. However, realize that you can get asked about the reverse reaction. A lot of the reactions, especially as we move through the third quarter here, we're going to be looking at reversible reactions. If that's the case, then we're just simply going to be reading it right to left, where the products are remaking the reactants. So how we're going to go about analyzing these potential energy diagrams has to do with a couple of main parts. Potential energy of the reactants is just simply how much energy do our reactions start with. So this is the point farthest to the left. The potential energy of our products is just how much energy do our products end up with. For a forward reaction, this is the point farthest to the right. We have activation energy, which you heard a little bit about with rates of reaction. So this is the minimum amount of energy needed to get the reaction started or going. If you don't have that minimum amount of energy, nothing's going to happen. This is the energy that's also needed to form the transition state from your reactants. So you have to get over this hump in order for the reaction to occur. We'll talk about the transition state at the very end of the video. It's just an intermediate step. The reactants have absorbed that activation energy, but they haven't fully reacted yet. The last part should sound familiar, heated reaction or delta H. This is just simply the difference in energy of the products and reactions, which we can read right off of the graph. We know that positive values are endothermic reactions, negative is exothermic. So just some simple things with just labeling, if you can fill this in on your chart. This would be representing an exothermic reaction. The products over here, over where I have the arrow, is lower than our starting reactants. So usually students don't have a trouble reading this graph in terms of values. Like if I ask students, how much energy do our reactants have? Most of them would probably be able to tell me 45 once you realize that this is our reactants. That energy is represented by line segment A, which is something that you need to be able to interpret even just for the Regents exam. The energy in my products, most students would be able to tell me is 10 kilojoules. Here's the line for their products. Here's 10 kilojoules. Well, that's represented by line segment B. Line segment B represents 10 kilojoules, so that represents the potential energy of our products. Some other important points, the top of our curve and the arrow on here is not perfect just because I was having some issues. So the top of the point is that's the transition state or the activated complex. You'll see both terms used. That's how much energy that transition state or activated complex has in between the 2 points. So in this case it would be 103 kilojoules. Well, the activation energy is how much energy it takes from our starting reactants to get up to that transition state. So that would be the difference of 103 and 45, which is represented by line segment D, our activation energy. The reverse reaction's activation energy would simply be going from the products back up in reverse to the transition state. So that would be our 103 minus 10 kilojoules, which is represented by the line segment that I have labeled E here. And then finally, our heat of reaction, that difference between the products and the reactants. Well, here are our products minus our reactants. So 10 minus 45 kilojoules would give me negative 35 kilojoules as my heat of reaction, and that's represented by line segment F. So you have to get comfortable with reading values off of this for all of these different things I've identified, but also being able to pick out the line segments, which again is sometimes the trickier part for students. Potential energy diagrams, you'll see some questions that involve the addition of a catalyst. You know from yesterday in the videos you watched that catalysts lower the activation energy for both the forward and reverse reactions. So our uncatalyzed reaction, which is the black line that you have on your note packet, is worth 200 kilojoules. I'm going from 50 up to 250, so when I find the difference, that's the addition of 200 kilojoules. For example, if I catalyze the reaction and it lowers the activation energy, say down to 200, and you'd have to be given some type of information about that, we'll see that now it only has to go from 50 to 200, so now I just have a difference of 150 kilojoules. So it lowers the activation energy, which remember increases the rate of the reaction. So see if you can take that for a second and just fill in this little practice set and see if you can identify using A, B, C, D, E, and F, the questions below. And then I'll just have you check it. I'll mention a couple things, and then we'll just talk about the last little part. All right, so let me have you check over your answers here. It's all, again, just identifying different line segments, looking at where your reactants and products are and the differences between the different pieces of this. So let me see if there's any that I think might trip you up. One might just be, again, the activation energy and heat of reaction, I think, in particular. Line segment B here is that difference of the reactants getting up to the top. That's the hump that they need to get over. So that would be the activation of the forward reaction. F is that heat of reaction, which is the difference between the products and the reactants. Now just realize that the heat of reaction for the reverse reaction is also represented by F, but in this case, instead of being a positive value for the forward reaction, it would simply be a negative value representing the exothermic reaction. So if a forward reaction is endothermic, the reverse is going to be exothermic. All right. You're going to do a whole bunch of practice in this. I posted some other videos for you to watch just to help you understand this, since obviously I'm not there right now to help you. But I did want to also mention lastly for your set of notes for today is just this idea of transition state theory, which you can go into chapter 16 for. This just has to do with that idea of this transition state when we look at potential energy diagrams. So this is kind of just in the middle of our reactants and our products. We think of it as a very unstable species that contains partial bonds. So it's like some bonds are starting to form as some bonds are starting to break, and it's the energy involved. So if we look at, sorry about that, the reaction between these two species, this is where we're starting at and this is where we're ending at. So we have the OH group that's going to bond with carbon as the Br is going to break off into an ion. So you can see here that carbon, this bond here would be starting to break in the transition state, and as well as at the same time, the carbon is starting to create a bond with oxygen. So it's the idea of, as you go through this potential energy diagram, here there's separate reactants. Here the OH is starting to approach the carbon. Here we have that transition state where, again, a bond is kind of partially being broken and partially being formed, and then they have fully reacted and overall energy is released in this case. So just again, this is just a theory. We can't isolate it of what we believe is happening in order to kind of start to explain this idea of this increase in energy, the top point of that hump. And then when we talk about some reaction mechanisms later on in this unit, we'll come back to this idea. One question on the textbook that I think is a good one to look at is this sample problem 16.9. Where it has you draw a reaction energy diagram in transition state. So it's talking about a reaction between O3 and an oxygen atom to make 2 diatomic molecules of oxygen. So it tells you that the activation energy of the forward reaction is 19, that the delta H for the reaction as written is negative 392 kilojoules. It wants you to depict this and also predict a structure for what you think it might look like. You need to be able to calculate the activation energy of the reverse in order to set up your diagram correctly. So see if you can pause it and just try this out on your own for a little bit, and then see if you can check it below, which, if we check it below, hopefully you took a second to think about it. Your delta H, if you think about analyze the potential energy diagram, can help you get to, along with your activation energy of your forward, the activation energy of your reverse. So that would give you, for your reverse, 411 kilojoules using those 2 values. The reason why I'm pointing that just helps you set this part up. You can see how, here's my delta H, which would be, again, involving your reactants and products. You have your energy of your forward reaction being 19 kilojoules, and then that would drop off to 411 kilojoules. What I find interesting is this transition state. So you would have this molecule of O3 that was initially formed. This bond is starting to break, and then that additional oxygen atom is starting to form a bond with that oxygen, and so that's starting to form. So that's just, again, an idea of kind of how you can see how the 2 are coming together and how you have a partial bond breaking and a partial bond forming. All right, so please go watch the other videos and then try out the practice as best you can, and hopefully we'll kind of just work from there.